Okay, so far we've tried to solve the Laplace equation in a rectangular domain. So x goes from 0 to 4. Oh, it's actually taller than it's wider. So it's more like 0 to 4, then 0 to 5. Here's the rectangular domain that Laplace of u is equal to 0. And I had an example, well, this value was a little different, but I had an example where it was 0, 0, 0, but this was non-zero. So you have a non-zero value up here and then 0, 0, 0. And then I also solved an example where this was y. What's that? 0 comma y. X is 0. X is always 0. So 0 comma y would be over here, right? So if you have the values as y here and then 0 everywhere, then we were also able to solve this, right? So, and then I also gave you some intuition behind what Laplace differential equation is. It's the time limit infinity to get a stabilized solution of the two-dimensional heat equation. So if you had like a heat distribution that's 0 here and 5 here, and then it's a straight line, that's 0 everywhere there, then you can kind of think about the weird-looking heat distribution you will get if the temperature is stabilized. So that's something that you can think about. So in my mind, the solutions probably look something like that. Something like that. All right. But then what I want to talk about is how would you solve it if it's not the case that 3 of these are zeros? See, in all our examples, you saw that how important it is to have at least 3 of these 4 boundaries being zeros, right? That was the only way we could get the Sturm-Liouville and sufficient initial condition to write down what we wanted. So now I have to explain to you how we can solve this in general, even if these are all non-zero. So let's say this is like a function of y, another function of y, and then here's a function of x. Let's call that g. Let's call it g1, and let's call this g2 of x. Because I replace y by 5, this is no longer a function of y. It just depends on x, so it's a function of x, right? So if you have such a thing, how can we approach such questions? Well, here's the idea. You set u as w1 plus w2 plus w3 plus w4, where w1 will be the following equation. W1 will be also satisfying the Laplace equation, right? But w1 will be only agreeing with u for 0y. The other cases, w2, 4y will be 0, w3, x comma 0 will be 0. Oh, why did I put x equals y? And then w4, no, these are all w1s. w1s, w1 of x5 would be 0. You can definitely solve this, right? Okay. Now, if you understood where I'm going, you should be able to tell me what w2 would satisfy. w2 would still be satisfying the original Laplace equation, but the boundary conditions are like what? w2 of 0y would be 0. w2 of 4y would be f2 of y. And then w3 of x0 would be 0. W2, sorry. W2 of x5 would be 0. Okay, and then, so you have this, and you have W3 would be satisfying the Laplace equation, and then W3 of 0y would be 0, and then W3 of 4y would be 0. W3 of x0 would be G1x, and then W3 of x5 would be 0. Okay. And then W4 would be a solution to the Laplace equation where the boundary conditions are this is equal to
G2x.
G2x. And each of these 4 questions can be solved separately, don't you agree? You can solve this, you can solve this, you can solve this, you can solve this. Not only that, if you add them up, because we're asking for the Laplacian to be 0, if you define u to be this, then what's Laplacian of u? This is Laplacian of W1, Laplacian of W2, Laplacian of W3, plus Laplacian of W4, and all of these are zeros, so it's going to equal to 0. So this u is definitely going to satisfy the original one, right? And then imagine what u of 0y would be. This would be W1 0y plus W2 0y plus W3 0y plus W4 0y. What's W1 0y?
F1.
F1y. What's W2 0y?
0.
0,
0.
0, 0. So it's going to equal to F1.
Oh yeah.
Y.
F1y.
So you can see that if you start doing this for all of the boundary conditions, then you recover all of these conditions, right? You get that? So by doing that, we can solve Laplace PDE for the case when you don't have 3 zeros. You can have just all of them non-zeros. You can still solve it.
Yeah, it's going to take very long.
It's going to be quite long, yes, yes. But it's doable.
Are we going to have any question on the midterm?
Actually, surprisingly, yes, but I'm going to show you a neat trick, okay?